Now, there's a couple things I want to make sure is understood before we get started today. The first of these is that, okay, you're not going to be here in the spring, right? You're graduating, right? Okay, and I believe so is Jesus and James. I believe all three of you are graduating. So I'm not going to spend a lot of time on this. What the phone conversation was this morning was that evidently enrollment is way down for spring. Now, I don't think that's the fault of anybody or anything. I believe it's the environment we're in. We're in COVID. Students are not comfortable. Faculty are not comfortable. No one's comfortable. And counts are going up. Things are almost out of control. And here we are worried about spring term, as well we ought to be. But here's what their solution is: bringing all faculty onto campus next week so they can register students. Well, number one, we can't register students because this new package banner does not allow us to register students. All we can do is advise students. They have this virtual advising center out there. I have hardly heard a peep out of the virtual advising center all term. They should have been focusing on virtual advising center and getting students in there. They haven't been, that I can tell. Have you been getting things about virtual advising? Yeah, because you're not coming back next term. So I can understand that. But so they're bringing us back to campus. I can't go back to campus because of my health situation. They don't want me back, which is good. I'm glad for that. But they're bringing everybody else back to be exposed, to do all this stuff, and we can't register a single student. You know, we can advise, but we could do that virtually. I don't know what's going on, but anyway, that's what the conversation was about this morning. That's what the meeting's about right after this class is over with, and so on. Now, the other, I think you heard yesterday, good news, bad news situation. The bad news is, unfortunately, wait, let me get James in here first, and then I'll make that announcement. I think he's heard it too, though. All right, so James is here, and so we're just missing Jesus. James, can you hear me yet? Okay. Let me just verify. Are you returning to campus in the spring, or are you going to transfer? Okay. All right. Congratulations. Way to go. There's a big push now to get students to register for spring term. Neither you nor Kira will be here in the spring, so you're exempt from this. I'm pretty sure Jesus is graduating too, isn't he? Or do you know? Yeah, I think so too. So it really doesn't make any sense for this class for us to talk about that, except other students who are enrolled. Please encourage them to go on and register. Register now. Don't wait until next week. Register. If they want to wait till next week, they can, but the big deal is to register. The second piece of information is that it's the good news, bad news situation. The bad news is tomorrow is a holiday. It's a state holiday, Veterans Day. The college will be closed, no classes, nothing going on tomorrow. But the good news of that is it doesn't affect us in this class any. It affects us in the other two classes y'all are in, but it doesn't affect us in this class. Okay, so that brings, I think, everything up to date. Do you have any questions, issues, problems, or concerns? Okay, I couldn't quite understand all that. Something about last week and yesterday. Right, yeah, I think Ryan told me that, and that he didn't specify, and that's fine. I didn't need to know. What I'd asked him to do is see if he could get in touch with Jesus, and he thought I said James, I guess. because Jesus looked like he had tried to come on but couldn't get in, so I was trying to encourage him to. No, it wasn't. It was Jemanuel. It was Jemanuel. I had asked him to, and he thought I said James. Maybe James Mullins, and I said Jemanuel, but whatever, because Jemanuel had kept seeing him pop up to come in the class. As soon as I'd let him in, he'd disappear and then pop up again, and I couldn't get him in. And I wanted someone to contact him and let him know, I'm trying to let you in. I don't know what's wrong. But that's why he contacted you. I understand. I know you don't miss class if you can help it. It's just that Jemanuel was trying to get in and I couldn't get him in. Sorry about that. Okay, but glad you're here today. But don't bother coming tomorrow, okay? Okay, because there are no classes tomorrow, which I think my body needs a rest. And so we're going to try to take it easy tomorrow. All right. If there's no other questions, we're starting today in chapter 4, which also means that I didn't get this done last week because as soon as, okay, let me back up. James, you were here on Friday, right? Right? Okay. We finished right, and we finished chapter 3 on Friday. I had hoped and planned to get the class posted on YouTube, but the computers were very, very slow. Internet was slow. Everything, I don't know what was going on. Maybe all the counting for the elections result. I don't know what was going on. I could not get it done. We had to leave to go out of town where we were, had terrible internet service, so I couldn't load the class that we had on Friday until yesterday, but it did get loaded then. I had also planned, since we finished chapter 3, to load the test for chapter 3. I couldn't get that done either, so I did that yesterday. Now it's under last week's stuff, I think. I don't believe I put it under this week. I believe I put it under week 12, which was last week, is where you'll find the test. Now I didn't get it posted under messages. I only posted it under test 3 under week 12, I believe it was. If you can't find it, or if it's inconvenient, if you can't read it or something like that, let me know, and I'm going to try to, when I have a chance. And now with all this stupid stuff they got with the registration stuff, I don't know if I have a chance, but I'm trying to get it posted under Blackboard Messages as well. I had planned to put it there, but I just ran out of time last night and also ran out of energy. This anemia is just really racking me. Though today it's felt better than most other days, so I'm hoping I'm coming out of it. But like right now, I've got a headache. Things are not going all that well with it, but better than it could have been. Okay, so let's go. So those are the announcements. Anything else before we start in chapter 4? Okay, chapter 4, the title is Vector Spaces. Okay, now this is a long chapter, 8 sections. Basically can tell you we're not going to finish all 8 sections in this term. It's a very long section. We'll get as far as we can. Your last test will be your final exam, and that will be just based on as far as we get in chapter 4. So let's hit it and go as far as we can. Section 4.1 are vectors in Rn. Okay, now I say it like that. That's not really probably the best way to say it, but I can't think of a better way to say it. When I say Rn, this is what I mean. Capital R, and it looks like it's raised to the nth power. Okay? Now, what the R stands for is the real number system. Okay? Now, here is something you probably remember from way in the past. That's a number line with, say, zeros somewhere in the middle here. 1. This pen is not writing well. I have to really slow down to make it right. Okay, negative numbers on this side. This would represent R1, the real number line in one dimension. So this is 1, 2, 3, 4, 5, 6, 7, and so on. Negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, and so on. Okay, that's R1. Now, pick me a color. Lavender, red, pink, brick colored red, yellow, orange, brown, light green, bright green, dark green, light blue, middle blue, dark blue. Pick me a color, any color. Anybody? Let me do red. That usually is one people will say. If we include a number line going up and down, and this would be 1, 2, 3, 4, and so on, -1, -2, -3, -4, and so on. This represents R2. Real number line perpendicular to each other, two number lines, that's R2. That's a plane. A plane represents R2. If, however, and this really gets messy, if you had a third dimension here, so this now, oh, I probably should have done another color here. Let me pick, or y'all pick a color if you want to. How about dark blue? Would that do for you? This is such an aggravating system. Okay, I'm going to pick dark blue here. And this dark blue is going to extend this way and back into the board like that. Okay? And this will be 1, 2, 3, 4, 5, -1, -2, -3, -4, -5, and so on. Okay? Now, I'm going to have to shift axes around too. This becomes my X, this becomes the Y, and this becomes the Z now. Okay? That represents R3. Three-dimensional space. The real number line extending into three spaces. Now, what in the world do we mean by Rn? I can't picture this for sure unless that n is 1, 2, or 3. But R to the n would mean the real number line in n dimensions. Okay? N dimensions. Okay? Now, I can't picture more than 3 because I live in 3 space. I can't imagine 4 space or 5 space or 6 space or n space. But that's what we're talking about, vectors in Rn. That's what 4.1 is telling us. Now, let's go back to our number line, the R1. Okay, if I can get my pen to show up here. This is sort of, there it goes. Okay, let's go back to black here. Pick a value anywhere on there, like right here. That is 3. Okay, that value is 3. You only have one dimension. You only have a one-dimensional thing. That's a +3, meaning you're going from the origin to 3 in one dimension. Okay, If, however, we were talking about a point up here, okay, in two-dimensional space, and I should have changed the color here to be red. This is so aggravating. Okay, a point up here that's red. This represents a vector here. This has two dimensions, 2, 3. You have to have two dimensions. So R2 has two dimensions. R1 has one dimension. R3, of course, would have to have three dimensions. Okay, so that could be 2 on the x-axis, negative 4 on the y-axis, and positive 1 on the z-axis. So that, whoops, in the wrong color. This is the blue. Okay, something over here, what did I say? I don't even remember now. 2 on the x-axis, minus 4 on the y-axis, and up 1, or here, I think that's where I was, up 1 here. So this would be 2, no, I think that was a 1. 1, comma, minus 4, comma, 1. Okay, that would have represented R3. There's R3 here, 3 dimensions here. So R to the nth would be, and I'm just going to give generic names for this, x sub 1, x sub 2, x sub 3, x sub 4, dot, 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 all the way up to and including x sub n. You would have to have, God, this is so aggravating. Okay, here's Jesus. Perfect attendance today, folks. Way to go. All right. Jesus, if you're in now, we were talking earlier about whether any of you would be back in the spring. I think your answer was you hope not, that you hope to graduate. Is that right? Okay, so you're not going to be registering for spring term, right? Not here. Okay, that's what my memory was. Okay, so I was saying before, I got interrupted this morning before my first class, made me late for my first class because there's a huge push now to get people to register for spring term. But the 3 of you are not coming here in the spring, so you don't have to worry about it. But that's what they were talking about. So if you start hearing or seeing or getting messages about that, you can ignore them because y'all are graduating and moving on to a 4-year school. But the second issue is, I don't think you heard this yesterday. I don't know if you realize this or not, but tomorrow is a holiday. It's Veterans Day. I think we're one of the few states in the country that celebrates this as a state holiday. So there are no classes tomorrow. That means we don't have Cal 3. We don't have differential equations tomorrow. But for this class, it doesn't matter because we have class on Thursday, so we'll have class both days here. The other thing I mentioned was that we did have our makeup class on Friday. James and I did. I did record it. However, I couldn't get it loaded before we had to leave town, and we were out of town where there's terrible internet, so I couldn't get it loaded there either. So I loaded it yesterday, so it should be out there on YouTube video. Under the playlist is there on that week 1 material. And that did finish chapter 3 for us. So I also posted the third test, and I think I posted it under last week. I didn't get it posted last week, but I posted it under last week's week 12, I think it was. So that's where you'll find it. I did not get it posted under Blackboard Messages. I'll try to get that done today if I can. But today is looking like a crazy, crazy day, because 15 minutes before this class is over with, I've got a meeting, and so I'll be late for that one. And then once that meeting's over with, I got another meeting, and then I've got at 3:15 my next class that goes until 7:45. So this is going to be a terribly crazy day. It started out that way, is continuing that way. This is the first class I've been able to start on time today, and now I'm wasting time explaining it. So what we're talking about here is vectors in Rn, and I was explaining what in the world Rn was. And here's what it was. R superscript 1 is the real number line. However you draw that, this real number line with all the numbers, real numbers in it in the world. To identify a number on the number line, just pick the number. -4, +3, 7, 1, 0.5, 1.5, -1.5. All you have to do is designate a single number, and that represents that place on the number line. That's R1. R2 is the two-dimensional space. Now the black axis is the x-axis, the red axis is the y-axis, okay? To specify a point there, you go right 2, up 3. That specifies a point in R2. Two coordinates, 2, 3, okay? Three-dimensional, you bring the x-axis out this way, y-axis goes back this way, z-axis up this way. That now represents a point in R3. And the one I chose was over here, where x was 1, y was -4, and z was +1. Okay? Or maybe that should have been a 2, -4. Maybe that is right. Let me go back and change that. I think I had it as 2 before, and then I changed it. If I could get my pen to show up. Where are you, pen? I've got it turned backwards. Okay? Yeah. So let's make this, I don't know why it's dragging all over the board. 2, -4, 1. You have to have 3 components to identify a point in R3. What is Rn? I can't visualize Rn, but it's the real number line in n dimensions. So if you were picking a point somehow on that, which I can't visualize, that'd be x of 1, x of 2, x of 3, x of 4, ... all the way up to x of n. And then there is where I was trying to draw a parentheses, and it was dragging my whiteboard all over the place. So that's a little bit better. That's what not sub n, Rn is. All right. Now, beginning in page 152, 4.1, vectors in Rn. In physics and engineering, a vector is characterized by 2 quantities, length and direction. That's what we mean by vector. Okay? It's represented by directed line segment. Here's one right here. This is, well, where in the world is, well, I'm on the wrong board. Okay, here's one. This red one right here, there's a vector. It's going from the origin up to the point 2, 3. There's a vector going from 0 to 3. Here's a vector going from the origin to 2, -4, 1. That one right there, that vector there. This one up here, however that represented, however you can imagine that to be here, that would be that point there. That's a vector in Rn. I can only draw it in 3 space because I don't go any further than 3 space. So a directed line segment has both the magnitude, that's a length, this one would be 3, this one would be something else, this one would be something else, this one would be something else. And it has a direction. This is heading this way, that one's heading that way, this one's heading this way, that one's heading somewhere. Okay, directed line segment. Line segment means fixed in length. Okay, directed means in a given direction. In this chapter, you will see that the geometric representation can help you understand the more general definitions of a vector. So I'm going to clear this because that's so messy, and we'll try to do something closer to what the book has. Geometrically, a vector in the plane, so the vector in the plane would be, I'm going to go back to my black, I believe. Okay. Let's just picture that we're in, well, I like to be more general than the book is. So here's the vertical axis, which we often call the y-axis. Here's the horizontal axis, we often call the x-axis. Okay? Now, geometrically, a vector in the plane is represented by a directed line segment with its initial point at the origin. And if you notice back in that previous one I did, every one of them started at the origin, no matter which direction we were in. Okay? With the initial point at the origin, terminal point at some value x1, x2. Now we could have called that xy, x2, okay, but the book chose to call it that. So there is its magnitude, is the length of that vector, and the direction is so many units on the horizontal axis, x1, so many units, x2 on the vertical axis. Okay? Now we represent this as x, and in the book that would be bold. I can't write bold, so I write that with an arrow over it. Sometimes it'll have two wings, sometimes just one. That's a vector. Now, the vector is different from its magnitude. Any vector of that length, anywhere in the plane, would be magnitude, same magnitude. But this one is pointed in a given direction, so it's the magnitude in a given direction. Okay. Now, this is called, and this is aggravating, when you want it to write, it writes, and when you don't want it to write, when you want it to write, it won't write, and when you want it to write, it writes. I don't know. So this is an ordered pair. Two coordinates define that vector. Okay? This is called the terminal point here. Okay? Also represents a vector. Now, if you haven't noticed it yet, when you were in pre-calculus algebra, which I assume all of you took here at Lawson, we used a book by Ron Larson. Okay? Then, when you got into calculus, we used a book by Ron Larson. I think Larson and somebody else, Bruce or Green or somebody. But anyway, he was the main author. And where we're in linear algebra, we've got a book by Ron Larson. Okay? Our differential equation is by Zeal or somebody, somebody like that, not by Ron Larson. Okay? Now, I sort of like Ron Larson because he gives us for instance, linearalgebra.com, LarsonLinearAlgebra.com. He gives us calcchat.com. In the other books, he also had calcview.com. And the other books had LarsonPrecalculusAlgebra.com and LarsonCalculus.com. So he gives all these great resources available to you to use. Okay? One thing that kind of bugs me about Larson, there may be a couple of things, but they bug me about most authors, but this one is it. When he's representing a vector in pre-calculus algebra, in pre-calculus trig, in calculus, he represents the vector as component notation x1, x2. That's the angle brackets representing this is vector x. Okay, vector notation here, vector notation there. When he's representing it in linear algebra, he uses the same notation he uses for a point, parentheses. So when you look at that, you don't know if he's talking about this point x or he's talking about the vector x, because he uses the same notation for both of them. Okay, so get used to that. Sometimes I'll still write it as an angle bracket. He never uses an angle bracket in this text, and I don't know why. Okay, but he chose not to. That same ordered pair is used to represent the terminal point, also represents the vector, that is x is equal to, this is point x is equal to that, and that looks just like vector x is equal to that. They look identical. You just have to know from context whether he's talking about the point x1, y1 or the components x1, y1 of the vector x. Okay? Now, the standard kind of notation here is vector u would equal, and again, I want to put an angle bracket there, but he does u1, u2, parentheses, that's the part that sort of gripes me. Vector v or x would be v1, v2. Okay? Vectors have the arrow over them or bold in your book. The components of a vector do not have bold or arrows. They're just numbers. Okay? Now, that looks the same as a point, u1, u2, but by context here you understand it's a vector. Alright, so let's move on to example 1. So I'm going to clear this if I can. Okay? So we're going to be mostly in R2 right now, meaning 2 space. To represent the vector u, 2, 3, what we do is draw your axes, a vertical axis or something close to that, and a horizontal axis or something fairly close to that. Okay? Now, tick off a few points here. And we don't need to go back here, but I'll do it. These are not very evenly spaced, and they're not very straight lines. They're not very horizontal or vertical lines, but just live with me. Okay. Let's just imagine each of those are evenly spaced. So to represent the vector u, 2, 3, I happened to use that one before, not realizing they were using it here. This is vector u with components, not coordinates, but components. U is 2, u1 is 2, u2 is 3. Okay, that would be the vector representing 2, 3. Let me see if I can make that look a little nicer. Okay, amazingly got that done. Okay, draw the directed line segment from the origin to the point 2, 3. Now to represent the vector negative 1, 2, we will go -1 up 2. So this would be vector v, and that would be represented by -1, and the pen is not doing well, 2. I hope that's right. Yeah. Okay. So they drew them on 2 different axes, but there we have them. Okay. That's what we mean by vector notation. Okay. Now, let's talk about vector operations. Now, I think all of you have had physics, right? Yay or nay? I assume so, but if not, you can probably live without it. But you probably run into vectors in trig. Those of you who were in my class, I know you did. Those that were in other classes, I bet you did, maybe even more than you did in mine. But you've run into this stuff before. So let's talk about one basic vector operation named vector addition. Okay? Now, I'm going to use, I think I'll use these same two vectors. If this is vector u right here, and this is vector v over here, if we were adding those together, you could take vector v here and put it on the tip of vector, this drives me nuts, on the tip of vector u, something like that, or put vector u on the tip of vector v. This would be the resulting vector. This is vector u plus v. Okay? Now, the book did dotted lines there, but that's okay. What would be the value of this? Add the x's. 2 minus 1, that would be 1. And 3 plus 2 would be 5. And it looks like, without even thinking about it, I almost got it exactly right. 1, 5. Okay? This is the vector, which is the sum of those two vectors, u plus v. This is so aggravating. Okay, u plus v. Okay. Now, all you do is add the components together. U plus v would be u1 plus v1, comma, u2 plus v2. And in our case, that would be 2 plus a negative 1, comma, 3 plus 2. And that would be 1, comma, 5, which is exactly what we got up here. Now, how do you do vector notation, vector addition? Add the components together. Don't go around drawing vectors like this. They're sloppy, they're messy. Maybe yours aren't as messy or sloppy as mine, but they still turned out to be pretty messy. And just add the components. That's the way to go. So let's do example 2, which is doing that very thing. So let's clear the drawings and find each vector u plus v. Okay? The first of these is vector u. I can't draw bold, so I put an arrow over it. Is equal to, and this is in 2 space, 1, 4. Vector v is 2, negative 2. I'm having to write so slowly it's about to drive me nuts. And also, my throat is going so dry I can hardly breathe. So if you don't mind, I drank all my water. Let me get a sip of a soft drink here. Let's see. We got about 30 minutes or more to go. I don't know if that did me any good. It sure felt good though. Okay. All right. I've got vector u and v here. It said find the vector u plus v. And I would say without drawing any pictures. What would be the first component? u plus v would be 1 plus 2, that would be 3, comma, 4 minus 2, that would be 2. Close it. That's it. Add the similar components together. Okay, 3, 2. Let's do the B one. And in B, U is 3, negative 2. V is negative 3, 2. And U plus V would be 3 plus a negative 3 is 0, comma, negative 2 plus 2 is also 0. Close. Now, this is an unusual vector. I'll tell you why I say that in a minute, but it's a necessary vector. Okay? Now, why did I say it's unusual? Because what was our first definition of a vector? A directed line segment that had both magnitude and direction. Can anyone tell me what the magnitude of the 0 vector is? 0, 0. 0 magnitude. It has no magnitude. What direction is it pointing? You can't even write down the coordinates for it. It's 0, 0. It's not pointing any direction and has no magnitude. And yet it's an essential vector that you would have. So it's an unusual vector, bizarre vector, doesn't fit some of the criteria of vectors, but it's absolutely necessary to have. Here's another. U is equal to 2, 1. And V is equal to, guess what? That good old 0 vector. 0, 0. What would be U plus V in this case? Two plus 0 is 2. 1 plus 0 is 1. You reproduce the vector u because the 0 vector doesn't change a thing. You move no units either direction. So that is u plus the 0 vector is always u. Okay. All right. They didn't write that last part, but you get it. Okay. I hope you get it. Now they did draw the parallelograms, they call them, kinda, okay, and I can't tell, for some reason my camera isn't indicating to me what you can see, so I don't know where this is, but I hope I'll be able to get close to it. There are the 3 vectors down there at the bottom, the sum of those 3 vectors. Okay, now if you can't see it, it's in your book on page 153. I wish I had more water. Okay, now that's the first operation with vectors, addition of 2 vectors. The second operation, another basic vector operation, is one called scalar multiplication. Now to multiply a vector v by some scalar c, scalar being any real number in the world, okay? Usually not 0, though you could do it, but it's usually not 0. You multiply each component of v by that number c. So if your vector v was 2, negative 2, I think that's what that one is, then multiply this one, pick a number c, any number in the world. 7. This would be 14, comma, negative 14. If this was 7, that would be minus 21, comma, 14. If this was 7, that would be 0, comma, 0. Okay, so nothing is going to change with the 0 vector. Okay, that's what scalar multiplication is. The scalar doesn't have to be positive. That scalar could have been a negative 3. This would have been a negative 6, positive 6. This would have been a positive 9, negative 6. This would have still been 0, 0. Okay, scalar numbers can be any number, not just whole numbers, not just integers, any real number. Okay, so I think I will write this one out for you because it is. If you have the number c, this is some scalar number, real number c, times vector v, that would be basically, think of this as c times the vector v1 comma v2, and you basically just distribute that inside. So that would be cv1 comma cv2. So every dimension must be multiplied by the same scalar number. Okay, so this would be exactly this. Now, goodness, I feel like I'm fading fast here. What it means by that, while they call it a scalar, this scales your original vector either up or down. Okay, so let's say if this was your original vector v, okay, and you multiplied it by a scalar c, if that c was greater than 1, like maybe 2, then you're going to double your x component, double your y component, so you basically double the vector. This would be 2v. Okay, or if that c was something less than 1, like 0.5, then this would have been exactly half of that. Okay, this would have been 0.5 v. Okay, okay, now, so that's where they get the term scaling. You either scale it up, scale it back. Okay, increase the length or decrease the length. There is one other thing you can do to it. If the scalar were negative, like negative v, that would be exactly the same length but in the opposite direction. So this would be a negative 1 v. Okay, so that gives you also a possibility there. You could have had this being any number in the world, negative 3/2. That would make it 1.5 times longer but in the opposite direction. So there's all sorts of possibilities there. Okay, now the one I just drew was negative v. Here was your original v here. Negative was exactly the same length but in the opposite direction. Now with that, if you were to add this vector to the original vector here, what you would wind up to is the 0 vector. Okay, oops, I did it again. When I'm thinking vectors, I usually write that vector thing. That would give you the 0 vector if you were to add negative v plus v, because negative v has exactly the same components of v except they're negative 1v, negative v1, comma, negative v2. It's exactly the opposite, and if you added that to v1, v2 to negative v1, negative v2, it comes out 0, 0. Okay? Now, with that in mind, what if you had vector u minus vector v. Well, just like we did when we were learning to add or subtract signed numbers, this is the same as vector u plus the opposite of vector v. Okay. All right. I am sorry. I'm going to have to get another swig of something here. The morning was going great until fairly recently. I'm just running out of steam fast. This anemia is just driving me nuts. Okay. So that's what we mean by subtracting two vectors, adding the negative of one vector to another. Okay, so let's do example 3. And guess how we do that? Adding the negative of 1? Just do it by components. That's the way to deal with vectors. Alright, so here's example 3, top of page 154. Let's let vector v be negative 2, 5. Again, we're in the plane, two-dimensional space. Vector u is 3, 4. Okay, perform each vector operation. Here's the A part. What is 1/2 v? That would be 1/2 of each of the components. 1/2 of negative 2 would be a negative 1. 1/2 of 5 would be a 5/2. There is the first part. Okay. The B part. Okay. The B part says u minus v. Vector u minus vector v. This would be 3, 4 minus vector v, negative 2, 5. Okay. I'm sorry. I am so tired. Okay. There's a couple ways you can do this. I think I'll try to just do it the simple way. 3 minus a minus 2, that would be 3 plus 2, that would be 5. Second component, 4 minus a 5, that would be a minus 1. That to me is the easy way to do it. Just do your components and do them exactly as you see them. They could change this to be 3, 4 plus, and then negate everything here, to negative 5. And that would do the same thing. That would be 3 plus 2 is 5, comma, 4 minus 1, and 4 minus 5 is minus 1. Okay. Now, that was pretty straightforward. They could perhaps even do it a different way. Looks like they did it pretty much the same way. Now let's do C. C is 1/2 v plus u. Alright, well, we've already done 1/2 v. 1/2 v up here was negative 1, 5/2, plus u was 3, 4. Okay, well, component by component. First component, minus 1 plus 3, that's a 2, comma, 5 halves plus 4. 5 halves plus 4. This is really 2.5 plus 4 is 6.5, and that would be 13 halves. I just couldn't think what would be the easiest way to do it. This would be 8 halves plus 5 halves is 13 halves. However you choose to do that. And that's what they got for theirs as well. Now, I am so tired. I know y'all are tired of hearing that, and I am sick and tired of saying it too, but I can't do anything with it right now. First question I had this morning from my boss was, did you see my email last night? I said, I was exhausted last night and I didn't see any emails. I was just trying to get ready for the next day. And that's exactly what I feel. I am totally exhausted. Okay. Now, I didn't draw any of our vectors here, okay? And I don't know where to hold it up because I can't see my image of that is reflected in my camera. So I hope you have books. If you don't have books or an ebook or something, you should be able to see how these operations that we just did worked. They don't show everything, but they show, I guess, enough. All right, now next is vector addition and scalar multiplication share many of the properties with matrix addition and scalar multiplication. Their names are so similar. The 10 properties listed in the next theorem play a fundamental role in linear algebra. Hint, hint, these are pretty important. In fact, in the next section, you will see that it is precisely these 10 definitions that help define what the title of this chapter is, vector spaces. Okay, so I think I will clear the screen. Any questions before I clear it? Okay. And mostly because I can't type bold, I think I'll write these out. I was hoping, because there's no subscripts and superscripts or other things, I might be able to type these, but they're bold and non-bold. So here's what we've got. Okay. First, U, V, and W are vectors. Okay. Vectors in the plane, meaning two-dimensional vectors. Okay. Now, also, C and D are scalars. Okay. U, V, and W have magnitude and direction going somewhere. C and D are just numbers, scalars, positive, negative, fraction, decimal, whatever, but they're just numbers. Okay. Now, the first of these properties that are really important is that U plus V, and you could have used U plus W or V plus W, it doesn't matter, but U plus V is also in the plane. I found if I write cursively, even though it's hard to read, it writes better than if I pick up, because the pen just does strange things when you pick up. Okay, now that has a title. This is the closure let's see how to say it. Vectors are closed under addition. And the pen just keeps messing up. Okay, vectors are closed under addition. And I'm sorry about the writing. It's really terrible. Now, what that means, if you have two vectors in a plane, same plane, obviously, and you add them together, the sum of those two vectors is in the same plane. That's what closure means. The addition is closed. Vector addition is closed. It's a strange way to say it, but that's what they'll use the shorthand. Here's another one. If you had the vector u plus vector v, that is exactly the same as vector v plus vector u. Okay? Now, what that means is vector addition is commutative. This is so aggravating. Vector addition is commutative. That means it doesn't matter which way you go. For instance, if I were driving to campus this morning and I drove the same way back this afternoon, the same distance is there. It doesn't matter which way you commute. As long as you go the same path, you're going to have the same distance. U plus V is equal to V plus U. Commutative property of vector addition. Okay? And that's sort of what they say in the book. They just say commutative property of addition, but it's vector addition. Now let's see if we can get number 3 in here. All right. If you added vector u to vector v and then added to that sum vector w, you get the same result as if you had taken vector u, sorry about this, I can't read, vector u plus the sum of vector v and w. Okay, yuck, it did it again. Okay, this is getting so tiring. Okay, what I was trying to write here is vector w. Okay, now what that means, if you first add vector u and v, now remember they're in the plane. They're all in the plane. U, v, and w all in the plane. You first add those two. That gives you a vector in the plane. Add another vector in the plane. That gives you yet another vector in the plane. That new vector in the plane is the same as if you had started with vector u in the plane and added to that the sum of v and w in the plane. You would get the same vector. And this is the vector, I like to phrase it this way, vector, and I can't get the pen to write, addition is associative. And the pen is just not writing at all well. Okay? That no matter how you associate the vectors together, as long as you're doing the same operations to them, you're going to get the same answer. So it's the associative property of vector addition. Okay, number 4. If I could find my pen. Goodness gracious, where does it go? There it is. So here's number 4. And this one we ran into earlier. If it's vector u plus, and we didn't name it before, plus vector 0, the 0 vector, that's always equal to vector u, because you're not adding anything to it. And this is in the plane. This would be u1 u2 plus 0 comma 0. That would give you u1 plus 0 is u1, u2 plus 0 is u2. You get 0, 1. Okay, that's called the additive identity property for vector addition. Additive vector identity for addition. Well, additive is in front. Additive vector. They call it property, additive identity property. Yeah, either way you want to do it. And the last of these that are on the addition side is this one. If you add a vector u to its opposite vector minus u, you're going to always get the 0 vector. Now, the 0 vector is the only vector that we put a number, bold it, or put an arrow over the top to give you that. Okay, most of the time they're letters that we use. Okay, and this is the additive inverse property. Okay, that's if you add a vector to its opposite, which is its inverse, you get the 0 vector. So those are the 5 that deal with vector addition. The next 5 deal basically with scalar multiplication. If I could get my pen to show up here, here's number 6. Now, just as we started up here, the sum of 2 vectors in the plane is also going to be in the plane. So this is the same deal. If you multiply c times vector u, this is also going to be in the plane, in the same plane as u. Okay, and this is closure under scalar multiplication. Okay, closure under vector multiplication, or scalar multiplication. We'll see later there's 2 other kinds of vector multiplication. We're going to call this one scalar multiplication. If u is in the plane, then cu is also in the plane. C could be an incredibly large number, but you're still in the same plane. It could be an incredibly tiny number, but you're still going to be in the same plane. So vector multiplication is closed, or scalar multiplication is closed. I keep wanting to call it vector multiplication. Okay, I need to find my pen again. Here's number 7. C, the scalar c, times vector u plus vector v. Okay, first, the sum of 2 vectors is a vector. We had that. And a scalar times a vector is just the scaled up of these. Now, what if you sum first and then multiply, that means that's the same as CU plus CV. Okay? If you get out, basically it's a distributive property. C times U plus C times V. And that's what they call it. I like to say a bit more than they do. I don't want to write it though. It's distributive law of scalar multiplication over vector addition. Okay, they just call it distributive law. So I think I'll just leave it like that too, because otherwise it's so hard to write. Distributed. I just can't write with this pen. Okay, that's one type, and I like to call that of scalar multiplication over vector addition. The next one is C plus D, these two scalars that we had up here, times vector U, I think it is. Yeah, no, yeah, U. Well, my pen was there and now it's not. There it is. Goodness gracious, where did that come from? You can't see it, but it just pulled up the lab I was working on before my 8:30 class this morning. And now I cannot get the, there we go, finally. Let's go back to our, there we go. Okay. C plus D times vector U is the same as C times U plus D times U. Here we had two different vectors adding together multiplied by a scalar. Here we have two different scalars added together multiplied by a vector. And they just say this is the distributive property. And since those are two different properties, why give them the same name? In my mind, they should say this is distributive property of vector of scalar multiplication over, no, vector multiplication, well, multiplication over scalar addition. Okay, scalar addition over scalar multiplication. It just seems like you need a few more describers there, and they don't use them. They just say this is also, here we go, a distributive property. It's a distributive property, but you're distributing different things. But first you were distributing scalar multiplication over vector addition. Now you're doing scalar scalar addition over scalar multiplication. Really is about the best we come down to. Now, the next one's a little bizarre too. If I could get the pen to show up. Where in the world is it? There. Nope. Every time I think I have it, it flies the coop. Can any? There it is up there. Okay, here we go. Okay. Here we have the scalar C times the scalar D times the vector U. Okay. That's the same as C times D, the two scalars multiplied together, times the vector U. Okay? Now, that is a type, a very limited type of the associative property, and that's all they say in the book, associative property of, and I would call that scalar addition over associative property of two scalars and one vector, I guess is how I say it. Associative property of multiplication of, I should have put that, of scalar multiplication with two scalars and one vector. Okay, strange to have to do it. All they say, associative property of multiplication. That's not very associative. It's very limited associative. Okay, now the last one, 10. 1 times vector u is vector u. Okay, because you multiply the scalar 1 by a vector u and you get the same components you had in vector u, that's u. That's the multiplicative identity element. Okay. Yeah, this thing just drives me nuts. Okay. Multiplicative property, multiplicative identity property. You can hardly read my writing. Just like in the real number system, 1 is your multiplicative identity element. 1 times 7 is 7. 1 times 4/3 pi is 4/3 pi. 1 times anything is that anything. Well, same thing holds here, is that in vectors, the scalar 1, that would be c or d equal to 1, times a vector u is going to still be that vector u. Okay, multiplicative identity property. Okay, now they do a little proof of a couple of these, and basically how do you do the proofs? Do them by components. Everything you do in vectors, do them by components. You do your proofs by components, you'll come up with the proof just about every time. Okay, now we just gone over. Y'all let me go over. Okay, I've got to get to a meeting, but we'll end it right there. We'll pick up next time on page 155, vectors in Rn. Did we get enough done to do some homework exercises? I think so. I think you can do number 1. It should be at Calc Chat. 3 or 5 should be at Calc Chat. 7 or 9 should be at Calc Chat. 13 through 15 should be at Calc Chat. 17 should be at Calc Chat. And stop there. We'll go up to R3 next time. All right, sorry that I went over, but boy, I'm running out of steam today. I've got to get to a meeting, so take care. Any questions, parting shots, thoughts, anything? Okay, we'll pick up then on Thursday just where we left off there. Okay, I've got to stop sharing so I can find how to get to the meeting. And so if I don't hear any objections, I'm going to end it for all of you, the last 2 of you. All right, take care. We'll see you on Thursday. Bye-bye.